Welcome to Dreamtime Science, where curiosity meets tranquility and knowledge flows like a gentle stream. Here we explore the wonders of our universe at a pace that soothes the mind. You know what's fascinating? I've been thinking about how something invisible, like radiation, can be all around us and yet affect us in ways we don't always notice. There's something remarkable about understanding how exposure works and what it really means for our health, kind of like uncovering a quiet secret of the world that's been with us all along. I'm excited to share some gentle insights that might change the way you think about this invisible presence in our lives. Should you find solace in these cosmic lullabies, consider becoming a regular dreamer by subscribing. Share what topics intrigue your curious mind in the comments below. Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. Long before humans dreamed of splitting the atom or harvesting the sun's power, the world was already drenched in radiation. It streamed down in gentle tides from the sky, seeped from the stone and soil beneath our feet, and crackled through the air in invisible threads. We lived and breathed within a constant bath of energy, mostly oblivious, shielded by skin and bone, guided by senses that could not perceive this secret restless dance. Yet the story of radiation was always there, waiting to be uncovered, by curiosity, by accident, and by the steady light of understanding. Let us begin then, not in the bombastic glare of mushroom clouds or the humming core of a nuclear reactor, but in the quiet, dust-lit study of a late 19th century physicist. The year is 1895, and Wilhelm Conrad Röntgen, a German professor, is working late into the night with his tubes and coils. He is investigating cathode rays, those mysterious streams of particles that flicker through glass under electrical tension. But something unexpected happens. A faint, ghostly glow appears on a coated screen across the room, far from the direct light of his apparatus. What is this invisible force, able to travel through darkness, through the air, through solid black card? Röntgen realizes with mounting awe that he has discovered a new kind of ray, one that can pass through flesh and reveal the bones beneath. He calls it the X-ray, X for the unknown, and in the weeks that follow, he produces the first shadowy images of the human skeleton, uncanny and luminous. News of the discovery travels swiftly, igniting imaginations around the globe. Doctors see the promise of peering inside the body without a single cut. Artists marvel at the translucent beauty of the images. The public is both fascinated and unsettled. Newspapers run stories of bones revealed by magic rays, and parlors fill with the eerie fun of X-ray portraiture. For a brief, heady moment, the X-ray is both scientific miracle and popular wonder, a bridge between the familiar and the mysterious. Yet Röntgen's discovery is only the opening note. Within a year, Henri Becquerel, a French physicist, stumbles upon another secret. He is studying phosphorescent minerals, materials that glow after exposure to sunlight, hoping to find a connection between their glow and the new X-rays. One cloudy day, unable to conduct his experiment in the sun, he tucks a sample of uranium salt and a photographic plate away in a drawer, thinking little of it. Days later, he develops the plate and is astonished to find its surface blackened, as though a hidden hand had inscribed itself upon the emulsion. The uranium, he realizes, emits invisible rays of its own, requiring no sunlight, no external spark. This spontaneous, self-driven emission will soon be known as radioactivity. The term itself comes from Marie Curie, a Polish-born scientist working alongside her husband Pierre in the cramped laboratories of Paris. The Curies are drawn like moths to the strange new phenomenon. They labor for months, sifting through tons of pitchblende, searching for the sources of this mysterious energy. Their dedication is relentless, almost obsessive. In time, they isolate two new elements, polonium and radium, whose radioactivity dwarfs that of uranium. Radium glows with a pale blue fire in the dark, emitting energy that seems inexhaustible. Marie Curie will later say, "One never notices what has been done. One can only see what remains to be done." Her hands, marked by years of handling radioactive materials, bear silent witness to the invisible danger that shadows this new science. Radiation, it turns out, is everywhere, woven into the very structure of the universe. It is the energy released when unstable atoms decay, seeking a more stable form. Sometimes it is alpha radiation, a heavy, slow particle that can be stopped by a scrap of paper or the thin layer of dead skin on our hands. Sometimes it is beta radiation, a lighter, faster electron, able to penetrate deeper but still stopped by metal or plastic. Sometimes, and most haunting of all, it is gamma radiation, pure energy, a ripple in the electromagnetic field, capable of passing through flesh and bone and concrete before slowly losing its power. Each form is a messenger from the heart of matter, carrying with it both the promise of discovery and the threat of harm. But what exactly is radiation? To answer, we must look more deeply into the nature of atoms themselves. Every atom is composed of a dense, positively charged nucleus surrounded by a cloud of electrons. The nucleus, tiny and ancient, contains protons and neutrons bound together by the strong nuclear force, one of the four fundamental forces of nature. Yet even this formidable glue is sometimes not enough. In certain atoms, the balance between protons and neutrons is precarious. The nucleus strains under its own weight, seeking a way to release tension, to find equilibrium. When it does, it emits energy, sometimes as particles, sometimes as waves, flinging fragments of itself into the universe. This is radioactivity, the spontaneous transformation of one element into another, the unceasing search for stability deep within the heart of matter. Radiation is not solely the domain of the rare and the artificial. It is the heat that warms you when you bask in sunlight, the light that travels across interstellar voids, the very mechanism by which stars shine. In the core of the sun, where temperatures soar to millions of degrees, hydrogen nuclei are pressed together by gravity's relentless embrace. They fuse, forming helium, releasing prodigious amounts of energy in the process. This energy radiates outward in all directions, carried by photons, packets of light, across the vast, empty gulf of space, finally reaching Earth after an 8-minute journey. It is this ancient, ceaseless rain of solar radiation that powers photosynthesis, fuels the weather, and sustains nearly every living thing on our planet. Yet not all radiation is so benign. The same rays that illuminate our days can also burn. Ultraviolet light, a higher energy cousin of visible light, can damage DNA, etching errors into the genetic code. Farther still, along the spectrum, lie the X-rays and gamma rays, potent enough to ionize atoms, to break the bonds that hold molecules together. This is the double-edged nature of ionizing radiation. It can heal, as in the precise beams that target cancer cells, or harm, as in the invisible assaults that cause sickness and mutation. The everyday world is alive with radiation, though we seldom notice. Trace amounts of uranium and thorium dwell in granite countertops and the brickwork of old houses. Potassium-40, a radioactive isotope, is present in bananas, in your own body, in the muscles that contract and the neurons that fire. Cosmic rays, high-energy particles born in distant supernovae, zip through the atmosphere, sometimes colliding with molecules to produce showers of secondary radiation that rain down upon the Earth. Even as you lie still, listening to this story, thousands of particles pass through you every minute, each a silent traveler from distant realms. Radiation, then, is both ancient and intimate. It is woven into the fabric of our bodies and the stones beneath our feet. It is the gentle touch of sunlight on a winter morning and the slow decay of carbon-14 in the rings of a tree. It is the clock by which we measure the age of fossils and the silent companion of every breath we take. To live is to be immersed in radiation, to share in the energy that animates the cosmos. Yet, as the 20th century dawned, the perception of radiation began to shift. No longer was it simply a scientific curiosity or a plaything of the laboratory. It became a symbol of both hope and fear, a force to be harnessed or feared. Early on, radium was marketed as a miracle cure, its glow bottled and sold in tonics, face creams, even toothpaste. Spas offered radium water, promising vitality and health. The allure of the mysterious element was irresistible, its dangers poorly understood. At the same time, fiction writers seized upon the strange, invisible rays as a gateway to the unknown. In the popular magazines of the day, radiation became the engine of transformation, the cause of monstrous mutations and extraordinary powers. The superhero's origin story was often written in the language of radiation, a laboratory accident, a burst of cosmic rays, a spider infused with radioactive energy. For a generation raised on the promise and peril of atomic power, radiation was both a source of dread and a spark for the imagination. The Second World War would change everything. In the fevered rush of the Manhattan Project, scientists learned to unleash the energy bound within the nucleus. The atom bomb was born, a weapon whose power dwarfed anything seen before. In the searing flash of Hiroshima and Nagasaki, humanity witnessed the destructive force of nuclear fission, the splitting of heavy atoms into lighter ones, each division releasing a torrent of energy and a flood of radioactive debris. In the aftermath, radiation became entwined with the language of apocalypse, its name synonymous with fallout, contamination, and invisible death. Yet even in the shadow of mushroom clouds, radiation retained its promise. Nuclear power plants rose from the ground, their cooling towers sending plumes of steam into the sky. Here, the same fission that shattered cities was harnessed to boil water, to spin turbines, to light homes and factories. The atom was no longer just a weapon, it was a wellspring of energy, a beacon of modernity. But always there was a tension, a sense that this power, so immense and so poorly understood, could slip beyond control. In hospitals and laboratories, radiation found gentler uses. X-rays became an indispensable tool for medicine, allowing doctors to peer inside the body, to diagnose broken bones, to search for tumors. Radioactive isotopes were used to trace the flow of blood, to target cancer cells with pinpoint precision, to sterilize equipment and preserve food. Technetium-99m, a short-lived isotope, became the workhorse of nuclear imaging, its faint gamma rays painting detailed maps of the body's inner workings. In these quiet acts of healing, the atom revealed another face, not just destroyer, but healer, a subtle and precise instrument in the hands of skilled practitioners. We find then that radiation is not easily categorized as good or evil, blessing or curse. It is a force, indifferent to human hopes and fears, shaped only by the uses to which we put it. The energy that powers the sun is the same that can poison a cell. The rays that reveal a hidden fracture can also sow the seeds of illness. Our relationship with radiation is thus a complicated one, marked by fascination, reverence, and caution. As we move through the world, we carry with us the legacy of this discovery. The language of radiation has seeped into our culture, our stories, our dreams. We speak of glowing green ooze, of mutant creatures, of invisible threats lurking in the aftermath of disaster. Yet we also celebrate the clean lines of a radiograph, the gentle warmth of sunlight, the quiet hum of a reactor powering a city far into the night. The story of radiation is, in many ways, the story of our attempt to understand the unseen, to give shape and meaning to forces that lie beyond the reach of our senses. It is a story of ingenuity and error, of triumph and tragedy, of curiosity that refuses to rest. And as we follow its path, from the flickering shadows of Röntgen's laboratory to the grand fusion engines of the stars, we find ourselves drawn ever deeper into the heart of matter, searching for the secrets that lie within. Even now, as you settle into stillness, the world is alive with the quiet hum of radiation. The atoms in your bones resonate with ancient echoes. The photons that bounce from the book's page to your eye are the children of nuclear fire, born in the heart of the sun. The air itself stirs with the faint whisper of cosmic rays, reminders of a universe in constant motion. In the next act, we will peer more closely at the paradoxes and puzzles that this energy presents, tracing its journey through the tangled web of life. But for now, let the gentle glow of curiosity illuminate the darkness, and rest in the knowledge that every breath, every heartbeat, is touched by the radiant beginnings of the atomic age. Beneath the hush of night, as the world outside your window lies quiet and expectant, another world stirs, one woven not from matter and muscle, but from pure energy. Radiation, that silent and often misunderstood phenomenon, courses through the fabric of existence, moving unseen among atoms and stars, through our bones and the shadows in the corners of every room. It is not the monster of fevered dreams, nor the untamed force of comic book catastrophes. To truly know radiation is to step into a realm of subtlety, of quiet transformations and delicate balances, and to lay aside the cloak of fear so often draped over its name. Begin then by tuning your senses to a gentler register, for the language of radiation is written in the softest of whispers, a photon here, an alpha particle there, a neutron slipping through the seams of matter. The very word radiation conjures images of glowing green vials, of warning signs stamped with trefoils, of disaster zones and distant haunted cities. But this is the language of our anxieties, not science. In truth, radiation comes in many guises, most of which are neither dangerous nor rare. Indeed, without it, life itself could not exist. To unravel these unseen threads, let us first set aside the myth that all radiation is the same, or that it flows only from the barrels and heartbeats of reactors. Radiation, at its essence, is the transmission of energy through space or matter. It can be as gentle as the warmth that seeps from the sun into your skin on a spring morning, or as powerful as the invisible pulses that sweep from a distant supernova, crossing the light years to touch our tiny planet. The forms of radiation are many, and they differ greatly in character. Imagine for a moment a family of travelers, each with their own mode of passage and their own stories to tell. There are the photons, carriers of electromagnetic radiation, which themselves come in a spectrum of personalities, from the mellow, comforting warmth of infrared, through the colours of visible light, into the harsher lands of ultraviolet, and onward to the searing realms of X-rays and gamma rays. Each photon is a parcel of energy, defined by its wavelength and frequency, and their behaviour is as varied as a flock of birds in flight. Beside them stride the particles, alpha particles, heavy and ponderous, composed of 2 protons and 2 neutrons, the very core of a helium atom. They are formidable, but their journey is brief. The lightest obstacle, a sheet of paper, the outermost dead layer of your skin, halts them in their tracks. Beta particles are lighter, single electrons, or their mirror image cousins, positrons, flung from unstable nuclei. They can travel further, slipping through flesh and air, but still meet their ends in the embrace of matter. Then there are neutrons, elusive and slippery, capable of slipping through walls and bones if their energies are right. And finally, the loneliest of all, the cosmic rays, high-energy protons and atomic fragments hurled from the violence of ancient stars, forever traversing the gulfs of space. What binds these diverse forms together under the name of radiation is their power to deposit energy, to stir the molecules of matter, to change the very structure of atoms. But how they do so, and with what consequence, is a matter of degree and context. Not all radiation is created equal, and not all exposure is a death sentence. In fact, you are, at this very moment, bathing in a gentle sea of radiation, its tendrils threading softly through your life. Consider the world upon which your body rests. Deep within the rocks, the soils, the very air, lie ancient isotopes, uranium, thorium, potassium-40, each quietly decaying, sending forth particles and rays as they seek a more stable existence. This is the Earth's background radiation, the low hum of energy that has accompanied life since its first stirrings in the primordial oceans. Each second, thousands of these particles slip through your body, mostly unremarked, doing little or no harm. In fact, the average person receives about 2 to 3 millisieverts per year from natural sources, a dose so small that it passes unnoticed, woven into the tapestry of daily existence. But the story does not end with the bedrock. Look upward, and the sky itself becomes a source. The sun, our constant companion, bathes us in solar radiation, both gentle and fierce. The atmosphere, that thin blue cocoon, shields us from the worst of the sun's ultraviolet glare, but some slips through, a reminder of the tightrope walk between energy and danger. And then there are the cosmic rays, ancient travelers from distant galaxies, colliding with the upper atmosphere to create showers of secondary particles which occasionally reach down to the living surface. At high altitudes in the rarefied air above the clouds, pilots and passengers receive a higher dose, a subtle, invisible souvenir of flight. Even within the walls of your home, radiation is present. Radon, a colorless noble gas, seeps from the ground in some places, collecting in basements and closed rooms. It is itself the daughter of uranium, and its decay can, over long periods and in high concentrations, pose a risk to lungs and health. Yet even here, context is everything. Most homes harbour only trace amounts, and sensible ventilation keeps the danger at bay. The dose, as Paracelsus taught, makes the poison. It is easy perhaps to imagine that radiation is a purely external force, something that happens to us from without. But the truth is more intimate. Our own bodies are modest sources of radiation. Potassium-40, a rare isotope of the element found in bananas, potatoes, and yes, within our muscles and bones, decays quietly within us, a clockwork of atomic transformations that ticks on year after year. Every breath you draw, every meal you eat, brings a handful of radioactive atoms into your system, where they become part of the perpetual dance of birth and decay. This internal radiation is a legacy of the stardust from which we are made. Yet, for all its ubiquity, radiation is not a uniform threat, nor is it always a threat at all. The body is resilient, capable of repairing the minor nicks and scratches dealt by low doses of ionizing radiation. Our cells are equipped with molecular artisans, enzymes and repair proteins that patrol the DNA, seeking out damage and stitching it closed. At low doses, the harm is often repaired before it can take root, and the risk is vanishingly small. Where, then, does danger truly lie? To answer this, we must distinguish between types and intensities. Ionizing radiation, the kind with enough energy to knock electrons from atoms, creating charged particles, poses the greatest risk. It is this capacity to ionize that can, in sufficient doses, damage DNA, disrupt cellular machinery, or, rarely, trigger mutations that may lead to cancer. But not all exposures are equal, and the body's ability to recover is formidable. Visualize, if you will, the difference between a single drop of rain and a torrential flood. A drop upon your skin is nothing, refreshing, unnoticed. A flood may overwhelm, sweeping away the structures that stand in its path. So it is with radiation. A dental X-ray delivers a fraction of a millisievert, a dose so tiny that your body shrugs it off without consequence. A chest CT scan, a few millisieverts, still far below the threshold of acute harm. Only at much higher doses, hundreds or thousands of millisieverts, absorbed over minutes or hours, does the spectre of radiation sickness arise. Acute radiation syndrome, that spectre of the nuclear age, is rare, and its thresholds are well understood. It is not the sudden dramatic transformation of fiction, but a cascade of symptoms: nausea, fatigue, hair loss, and, at the most extreme doses, the failure of the body's most rapidly dividing cells, those of the gut, the blood, the skin. Death comes not as an explosion, but as a slow unraveling, the body's machinery failing from within. Yet such doses are encountered only in the direst of circumstances: nuclear accidents, unshielded reactors, or the detonation of a weapon. Even among the survivors of Hiroshima, Nagasaki, or Chernobyl, many received doses insufficient to cause acute illness, and those who did were often the first responders, the unwitting, the unlucky. The world remembers these tragedies with a kind of collective shudder, but they are the exceptions, not the rule. Even in the shadow of Chernobyl, the vast majority of people received doses only a few times above the background, enough to slightly elevate cancer risk over decades, not to cause immediate disaster. The fear of radiation, potent and enduring, often outstrips the reality. The unseen, after all, is the most unsettling. But the unseen is not always malevolent. There are places where radiation is not just tolerated, but sought out. In the spa towns of Europe, people once flocked to bathe in radon-rich waters, hoping for relief from arthritis and other ailments. In the highlands of Brazil or the steppes of Iran, natural background radiation is 10 times higher than the global average, yet no waves of mutation or sickness sweep through the populations. The body adapts, repairs, endures. To live, then, is to live with radiation. It is etched into our bones, in the carbon-14 that courses through our cells, in the gentle warmth of the sun upon our faces, in the starlight that travels across the gulf of night. Even our technologies, so often feared, are carefully measured and controlled. The radiation used in medicine for diagnosis or therapy is calibrated with exquisite care, balancing benefit and risk. In cancer treatment, precisely targeted beams of radiation are used to destroy malignant cells while sparing the healthy. The same force that can harm in excess can also heal. The myth of giant mutations, of monstrous forms bursting forth from the irradiated, belongs not to science but to the fevered imaginations of storytellers. Radiation, in truth, is a rather poor creator of monstrous change. Most mutations caused by radiation are subtle, often invisible, and rarely beneficial. The double helix of DNA is robust, and most errors are caught and corrected by the vigilant enzymes that maintain its integrity. Only in the rarest circumstances do radiation-induced mutations lead to noticeable changes, and almost never to the fantastical extremes beloved of pulp fiction. Yet the fascination lingers. Perhaps it is the very invisibility of radiation that gives it such power in the mind, a force that cannot be seen, tasted, or touched, yet is capable of changing the course of life itself. But to understand it is to take away some of its terror, to place it among the many forces that shape our world, neither wholly good nor wholly evil, but complex, nuanced, and above all, natural. So, as you lie in the gentle dark, let the knowledge settle like dust upon your thoughts. You are part of a world that pulses with energy, bathed in a constant, gentle tide of radiation. It weaves through the fabric of your days, mostly unnoticed, a silent partner in the story of life. There are dangers, yes, as with any force of nature, but also balance, resilience, and the quiet assurance that you are, and have always been a child of the stardust. Beyond, in the realms where atoms are split and energy is conjured from the heart of matter, a new chapter awaits, a story of human ingenuity, of harnessing the power of the nucleus, and of the choices we make as stewards of such potent forces. The unseen threads of radiation continue onward, leading us deeper into the labyrinth of discovery and consequence, where the light of understanding grows ever brighter, and the shadows begin at last to recede. There is a certain quiet thrill that settles over the laboratory as midnight deepens, a hush broken only by the soft tick and whir of hidden machinery, the occasional shuffle of paper, and the low, thoughtful murmur of a physicist lost in calculation. In that hush, in the gentle pools of lamplight illuminating benches scattered with glassware and wires, another, more ancient silence prevails, the silence of the invisible. For here, in this sanctum of inquiry, the human senses meet their match. Ionizing radiation, that mysterious flow of energy set loose from the heart of atoms, has no color, no taste, no scent. Even the most sensitive skin feels nothing as it passes. The world, to our eyes, is unchanged. Yet the need to sense the unsensible runs deep, for the story of radiation is not merely a tale of curiosity, but of consequence. There is wonder in the discovery that the universe is alive with unseen energies, but also danger woven into the very fabric of matter. It became a matter of urgent necessity to find ways to detect, measure, and tame these potent forces. And so, out of the yearning for knowledge and the imperative for safety, a new lineage of instruments was born, devices that would become humanity's eyes and ears in the unseen world. The earliest radiation explorers, those who followed in the wake of Becquerel, the Curies, and Rutherford, began with almost nothing. The first clues were subtle: a fogging of photographic plates, a faint glow in the dark, a chemical reaction uncannily swift. In 1896, when Henri Becquerel discovered uranium's peculiar property of imprinting itself on photographic film, it was not a matter of direct observation, but of inference, a ghostly image, the shadow of the invisible. For a time, this was the pattern. Radiation made itself known only by its effects, its ability to fog film, ionize air, or change the color of salts. But soon, more deliberate methods emerged. In the closing years of the 19th century, the British physicist Charles Thomson Rees-Wilson watched how charged particles passing through air could seed the formation of tiny droplets, making the path of the invisible visible. His invention, the cloud chamber, was a glass vessel containing supersaturated vapor. When a particle of ionizing radiation passed through the chamber, it left a trail of ions in its wake, upon which droplets condensed, miniature clouds tracing the path of the particle. These wispy lines, delicate and evanescent, offered the first direct glimpses of the atomic world. For the first time, the invisible left its signature in the air, like footprints across a dew-laden field. The cloud chamber was soon joined by its cousin, the bubble chamber, devised by Donald Glaser in the 1950s. Here, a superheated liquid, often hydrogen, stood poised on the brink of boiling. As a charged particle passed through, it generated a string of bubbles along its path, each one a microcosm of boiling, each a marker of a particle's journey. Photographs of these chambers became iconic: swirling, looping lines, collisions frozen in time, a silent ballet of matter and energy. Yet, for the practical business of detecting and measuring radiation in everyday settings, hospitals, laboratories, nuclear plants, a different kind of instrument was needed, something robust, portable, and reliable. Enter Hans Geiger and Walter Müller, who, in 1928, brought forth an invention that would become as emblematic as the stethoscope or the thermometer, the Geiger-Müller counter. At its heart, the Geiger counter is beautifully simple. A thin-walled metal tube filled with a noble gas, argon, neon, or helium, serves as the detection chamber. Running through the center is a wire held at a high positive voltage relative to the tube's wall. When a particle of ionizing radiation enters the tube, it collides with a gas atom, knocking loose an electron and creating an ion pair. That electron, propelled by the electric field, accelerates toward the central wire, smashing into more atoms along the way and sparking a cascade, a brief sharp avalanche of ions. This momentary surge generates a pulse of current, which is counted and in most familiar models translated into the iconic click that so many have heard in movies and television. Each click is a token of the invisible, a granular acknowledgement that here and now an atom has changed, a particle has passed. The Geiger counter became the workhorse of radiation detection, portable, rugged, and able to sense a variety of particles, alpha, beta, and gamma. Its ticking chorus became the soundtrack of exploration in uranium mines, hospital radiology wards, and the laboratories of nuclear physicists. But it was not without limitations. The Geiger tube, for all its virtues, could not easily distinguish between different types or energies of radiation. It told you simply that something had happened, an event had occurred, but not precisely what or with what vigor. For more nuanced measurement, other instruments stepped in. The scintillation counter, for example, harnessed the property of certain crystals, sodium iodide, cesium iodide, among others, to emit tiny flashes of light, scintillations, when struck by ionizing radiation. These flashes, invisible to the naked eye, could be amplified and counted by photomultiplier tubes, yielding not only a tally of events, but also clues to the energy of the impinging particles. Scintillation detectors became crucial in medical imaging, environmental monitoring, and high-energy physics, offering a richer palette of information. Then there were ionization chambers, elegant in their simplicity, a vessel filled with gas, 2 electrodes, and a voltage between them. As radiation passes through, it ionizes the gas, and the resulting charge can be measured as a current. Unlike the Geiger counter, which produces a sharp, digital pulse, the ionization chamber's output is analog, a current proportional to the amount of ionization, and thus to the intensity of the radiation. These chambers became the standard for measuring high levels of radiation, such as those encountered in nuclear reactors or during radiotherapy. Yet, as understanding grew, so did the need for precision and personal protection. For those who worked in the presence of radiation, it was not enough to know that radiation was present. It became essential to know how much had been absorbed, how much energy, delivered invisibly, had been deposited within their very cells. The concept of dose emerged, a measure not merely of radiation's presence, but of its biological consequence. To this end, the dosimeter was born. The earliest personal dosimeters were film badges, small packets of photographic film worn on the body, sometimes clipped to a collar, sometimes tucked into a pocket. Just as Becquerel had discovered with his uranium salts, the film would darken in proportion to the radiation it absorbed. After a period of exposure, the badge would be developed, and the degree of darkening compared to a set of standards, yielding a record of the wearer's cumulative dose. But film, though ingenious, was only a partial solution. It could record exposure only after the fact, required careful development, and was sensitive to heat and age. Newer technologies soon followed. The thermoluminescent dosimeter, TLD, made use of crystals, lithium fluoride, calcium sulfate, that when exposed to radiation trapped energy within their lattice structure. Later, when the crystal was heated, this stored energy was released as a faint glow of light, which could be measured and related to the amount of radiation absorbed. TLDs were robust, sensitive, and reusable, and quickly became a staple in radiation protection. Modern dosimeters now include electronic devices capable of providing continuous real-time readings, often with digital displays and alarms. Some even log data over time, creating a detailed map of exposure. In hospitals, nuclear facilities, and research labs, these badges are an ever-present companion, a quiet reassurance, a reminder of the unseen risks, and a testament to the power of measurement. But detection is only the first step. To study and utilize radiation, to work alongside it safely, requires not just knowing where it is, but understanding how to shield oneself from its effects. Here, the ingenuity of engineers and physicists meets the realities of biology and materials science. Each type of radiation demands its own strategies. Alpha particles, heavy, slow, and doubly charged, are easily stopped, unable to penetrate even a sheet of paper or the outer layer of skin. Yet, if alpha emitters are inhaled or ingested, they become potent hazards, delivering intense, localized doses. Beta particles, lighter and swifter, can travel farther, but a few millimeters of plastic, glass, or aluminum suffice to halt them. Gamma rays and their kin, X-rays, are another matter entirely. Massless, chargeless, and profoundly penetrating. Only dense materials, lead, steel, concrete, can attenuate their passage, and even then, thickness matters. Shielding is thus a dance of compromise, balancing practicality, cost, and protection. In diagnostic radiology, thin lead aprons suffice to protect patients and technicians from stray X-rays. In nuclear reactors, massive concrete walls, meters thick, encase the core, absorbing the torrent of gamma rays and neutrons. For astronauts in space, where cosmic rays sweep through with relentless energy, shielding is a constant challenge, driving research into new materials and clever configurations. But passive shielding is not the only defense. Time and distance form the other pillars of radiation protection. The less time one spends near a source, the lower the dose. The farther away, the less potent the exposure. These principles are woven into the protocols of every radiology suite and nuclear facility. Minimize time, maximize distance, use shielding. Simple, elegant, and profoundly effective. Yet, in the history of radiation, there have been moments of trial, times when the invisible escaped its bounds. The Chernobyl disaster, the Fukushima incident, the legacy of atomic testing, these were crucibles in which the tools of detection and protection were tested under fire, and in which new lessons were forged. In the aftermath of Chernobyl, teams of scientists and engineers entered the radioactive zone, Geiger counters crackling, dosimeter badges tallying their silent accounts. They mapped the invisible landscape, tracing the patterns of fallout, charting the zones of danger and safety. Their painstaking work, their careful protocols, became the template for all that followed. In Fukushima, too, the quick deployment of dosimeters, the establishment of exclusion zones, and the distribution of protective gear saved lives and mitigated harm. But even in less dramatic settings, the tools of radiation detection find their way into everyday life. Airport security scanners, smoke detectors, the testing of foods and materials for contamination, all rely on the quiet vigilance of these instruments. In medicine, the precise measurement of dose ensures that the benefits of radiotherapy and imaging are delivered safely, maximizing healing while minimizing risk. Clever experiments, too, have advanced the art of detection. Consider the technique of coincidence counting, in which two or more detectors are arranged so that only events occurring in both simultaneously are recorded. This allows scientists to filter out background noise, to catch rare and fleeting phenomena, such as the fleeting positron's annihilation signature or the elusive neutrino's ghostly passage. In deep underground laboratories, shielded from cosmic rays by kilometers of rock, detectors the size of cathedrals stand sentinel, awaiting the faintest whisper of dark matter or the sigh of a neutrino from the heart of a distant star. Protection, too, has grown more sophisticated. In modern nuclear plants, workers don not only lead aprons, but full-body suits, respirators, and electronic monitors. Robotics and remote handling equipment allow dangerous tasks to be performed at a distance, sparing human operators from exposure. Hospitals carefully calibrate every scan, every treatment, guided by protocols refined over decades. All of these tools, counters, chambers, dosimeters, shields, are not just artifacts of technology, but extensions of our senses and our will. They allow us to move with confidence through a world laced with invisible energies, to harness the power of the nucleus for healing, for discovery, for light. They are the quiet companions of every radiologist, physicist, and engineer who walks the boundary between the visible and the unseen. Yet the story does not end here, for as our instruments have grown more subtle, so too has our understanding of the balance between risk and benefit, between fear and promise. The invisible, once a source of dread and uncertainty, is now a realm mapped with precision, managed with care, and explored with wonder. And so, as the laboratory light still glows in the small hours, and the Geiger counter ticks softly in the hush, there remains one more chapter to unfold. The interplay of radiation with life itself, the intricate dance of energy and biology, and the unfolding promise and peril that lie ahead. There comes a point in any deep contemplation of the natural world when the subject at hand ceases to be merely an object of study and begins to reflect our own image back to us. So it is with radiation, a phenomenon that threads through the fabric of existence, invisible and omnipresent, yet as deeply entwined with human fate as the air we breathe or the starlight that falls upon us in the quiet of night. We have travelled far through the landscapes of its science, tracing rays and particles, watching atoms split and reassemble, marvelling at the ways in which this unseen energy shapes both cosmic and terrestrial destinies. Now, as dusk settles in the mind, let us allow our thoughts to drift further into the philosophical eddies that swirl around the very concept of radiation and our relationship with its power. Radiation in its essence is a story of paradox. It is the breath of the sun, the silent messenger that brings warmth and light to the cold surface of our planet, coaxing life from barren stone and water. It is also the harbinger of decay, the whisper of entropy that steals through matter, disassembling the old, making way for the new. It is both the healer and the destroyer, the force that can banish tumours from the body or sow the seeds of illness in healthy cells. It can light our cities for generations or render landscapes uninhabitable for centuries. In the heart of radiation is this duality, the capacity for unimaginable creation and for devastation beyond comprehension. The history of our species has always been entwined with forces we do not fully understand. Fire, once a terror and a miracle, became a tool, a servant, and sometimes an enemy. Electricity, invisible and capricious, was harnessed and tamed, woven into the fabric of modern life. But radiation, with its roots in the very structure of matter, is different. It is not just a tool or a resource. It is a window into the fundamental workings of the universe. In a photon's journey from a distant star, or in the trembling of a uranium nucleus on the verge of fission, we glimpse the same laws that shaped the first atoms in the early cosmos, and will one day unravel the last stars as the universe grows cold and dim. Consider for a moment the paradoxical gift of sunlight. Each morning, photons, packets of electromagnetic radiation, stream across the vacuum of space, traversing 150 million kilometers to wash the Earth in warmth and light. This radiation is ancient, born in the nuclear furnace at the sun's core, where hydrogen fuses into helium in a dance of quantum probabilities and raw energy. Without this ceaseless flow, our planet would be a frozen wasteland, devoid of life. The green of forests, the glint of water, the hues of dawn and dusk, all are the handiwork of sunlight, the gentle face of radiation. Yet even here there is danger. Ultraviolet rays, too intense or too prolonged, can damage DNA, sowing the seeds of mutation and disease. There is no escaping the double-edged nature of this force. The paradox grows deeper when we move from nature's radiation to that which we have learned to wield ourselves. The discovery of radioactivity at the close of the 19th century was a revelation. For the first time, we saw that matter itself could be a source of energy, that the very atoms comprising our world were not immutable, eternal, but restless, dynamic, and capable of transformation. The work of Curie, Becquerel, and Rutherford pulled back the veil, revealing a hidden world of alpha, beta, and gamma rays, of half-lives and transmutations. The atom, once imagined as the smallest, most indivisible unit, became a miniature universe, alive with possibility and peril. With this knowledge came power, more power than humanity had ever known. The splitting of the atom in the 20th century was both a triumph of intellect and a cause for profound unease. Nuclear energy promised a future of abundance. Electricity generated not from the burning of coal or oil, but from the rearrangement of matter itself. The dream was heady, a world lit by the invisible fire at the heart of the atom, a civilization freed from want by the almost limitless energy locked within ordinary rock. And to a degree we realized that dream. There are cities that hum with the quiet, potent energy of uranium and plutonium, their lights glowing long after the sun has set, powered by the controlled dance of neutrons in a reactor's core. But even as we built monuments to our mastery, we encountered the shadow side of this force. In the mushroom cloud rising over Hiroshima and Nagasaki, radiation revealed its most terrible face. In the silent, invisible fallout that drifted across continents during the era of nuclear testing, we learned that the reach of our inventions exceeded the boundaries of our foresight. The disasters at Chernobyl and Fukushima, though separated by decades and thousands of miles, both bore witness to the same truth. The energy that can light a city can also poison its soil and water, render homes uninhabitable, and haunt generations with invisible scars. So we find ourselves as a species in a place of profound responsibility. To harness radiation is to stand at the threshold of creation and destruction, to hold in our hands the power to heal or to harm, to build or to obliterate. This is not a burden to be taken lightly. The history of our engagement with radiation is a mirror, reflecting our ingenuity and ambition, but also our hubris and fallibility. One might wonder, in the quiet of the evening, what it means to live in a world saturated with such energies. Some forms of radiation are as old as the Earth itself. Natural radioisotopes in the ground, cosmic rays from distant supernovae, even the faint afterglow of the Big Bang, all are woven into the tapestry of our existence. Our bodies, too, bear traces of this legacy. Potassium-40, a radioactive isotope, decays quietly within our own cells, the same as it has for billions of years. We are, in a sense, creatures of radiation, born of it, shaped by it, and subject to its whims. Yet the radiation we create, the energies we unleash, are of a different order. They are not only natural, but technological, born of our curiosity, our restlessness, our refusal to accept limits. The medical uses of radiation offer hope and healing, X-rays that peer through flesh and bone, revealing the secrets within, radiotherapy that targets and destroys malignant cells, buying precious time for those who would otherwise be lost. Here, radiation is a scalpel, precise and life-saving, a testament to our ability to turn danger into remedy. But even in healing, there is caution. The line between medicine and harm is thin. Too much radiation, or radiation in the wrong place, brings sickness instead of health. The same rays that illuminate a broken bone or shrink a tumor can also damage healthy tissue, disrupt the delicate machinery of life. In our quest to heal, we are reminded again of the paradox. The very tools that save us can also hurt us if wielded without care. beyond medicine, the ethical landscape of radiation expands into questions of stewardship and justice. Who decides where nuclear power plants are built, and who bears the risk if something goes wrong? How do we weigh the promise of carbon-free energy against the enduring challenge of waste, spent fuel that will remain hazardous for millennia, far beyond the span of any human institution? What do we owe to those who live near uranium mines, or downwind from reactors, or in the shadow of past accidents? These are not questions with easy answers. They force us to confront the limits of our knowledge, the fallibility of our systems, and the need for humility in the face of forces we cannot fully control. Yet there is another face to this story, one that speaks not of fear, but of wonder. To study radiation is to peer into the heart of matter, to listen to the quiet ticking of atoms as they transmute, to witness the birth of elements in the fiery crucibles of stars. It is to understand, in some measure, the processes that have shaped our planet and our bodies, to see ourselves as participants in a cosmic cycle of creation and decay. Every breath we take, every morsel of food, every heartbeat, is touched by the legacy of radiation, by energies that have travelled across unimaginable distances and through eons of time. This awareness, if we let it, can foster a kind of kinship with the universe. We are not separate from the forces of nature, not mere observers, but participants in a drama that began long before our species arose and will continue long after we are gone. The photons that warm our skin are the same that once set life in motion. The atoms in our bodies were forged in ancient stars, scattered across space by supernovae, and gathered into the living tapestry of Earth. Even the dangers we face, the risks we take, are part of this larger story, a story of transformation, of balance, of the ceaseless interplay between order and chaos. In this light, the ethical questions sharpen, but so too does the sense of possibility. What if, instead of seeing radiation only as a threat or a resource, we came to see it as a teacher? What if the discipline required to manage nuclear energy safely, or to use radiation in medicine wisely, became a model for our relationship with other forces, climate, biodiversity, technology itself? To live with radiation is to accept both vulnerability and agency, to recognize that we are not omnipotent, but neither are we powerless. We are stewards, entrusted with a portion of the universe's energy, called to use it with wisdom and care. There is, finally, the question of legacy. The wastes of our nuclear age will outlast us, persisting long after our languages and cities have faded. How shall we speak to the distant future, to those who may stumble upon our buried caches of spent fuel or the ruins of reactors? What symbols will endure? What warnings will be heeded? This is a challenge unique to our time, a measure of our reach and of our humility. We are writing messages in the language of geology, carving our cautionary tales into the strata of the earth. And so, as the stars wheel overhead and the world turns quietly on its axis, we find ourselves suspended between awe and apprehension, between the promise of light and the shadow of danger. Radiation is both a fact and a metaphor, a force that shapes the world and a mirror in which we glimpse our own capacities for creation and destruction. In learning to live with it, we are learning too to live with ourselves, with our gifts and our limits, our dreams and our responsibilities. The journey is not finished. The energies we have awakened continue to ripple through the world, shaping lives and landscapes, raising questions that will echo into times we cannot yet imagine. And so, as night deepens and the mind grows quiet, we linger at the threshold, listening to the faint, persistent hum of the universe, aware that it is both within and around us, inviting us always to wonder and to care. As our gentle journey through the unseen waves of radiation exposure drifts to a close, may the quiet shimmer of understanding settle softly like a comet tail fading into the hush of space. Rest now in the calm glow of curiosity, and when your mind wanders back to the stars, return for more Dreamtime tales that light the cosmos of our wonder.